if you guys are evaluating f of 3, given that the function f of x equals x squared minus 1, we understand that this value for 3 represents the x value that's going into the function. As the function is defined up here of x squared minus 1, I know that x is getting replaced with 3, so it's 3 squared minus 1. Taking 9 minus 1, I'm getting 8 back. That 8 represents the value of the function as it's defined up here when x equals 3. I went on with this yesterday to make a point that this value for the function, since we're plugging an x value in, is also giving us an ordered pair, a point that we could plot if for some reason I wanted to consider the graph of this function. So the ordered pair would be 3 because that's what went in. 8 is what we got back. So with all that said, over here, if I know I'm taking an x value, I'm plugging in, I'm getting this value for the function back, that's the same thing as getting the value for y back, right? If I could eventually plot this on a graph. So if I go to my calculator and I look at the other values here for the function I have to consider, like f of 5, f of negative 1, and so on, now let's just punch in under y equals, let me clear this out of here. Under y equals, let's put our function in. Our function is x squared minus 1. Since we talked about this a little the other day, we know that we've got to have our table set up on ask. So to do that again, you do second window. You go down to the independent variable and make sure that's on ask. If it is not, you go over to ask, you hit enter to highlight it. And then we go to our table, which is second graph. If I want to find what f of 5 is, now that I've plugged my function into the y equals part, I just hit 5, I hit enter. F of 5 is 24. If I want to figure out what f of negative 1 is, negative 1 goes in, enter. F of negative 1 is 0. I want to plug in 0, get negative 1 back, plug in negative 2, get 3 back. So 24, 0, negative 1, and 3. If we're just evaluating functions for certain values of x, we can plug this function into the y equals form on our calculator, the y equals screen, and we can simply go to the table and just plug the x values in. It can be that simple. All right, we got a new defined function, f of x equals 2x squared minus 3. We're going to use that function. Well, to start off here, we're going to find f of a. Well, we know that this little part inside the parentheses here, that represents the x value that we're inputting into the function. So when I go up here to my function and I locate my x's, being just the one x right there, I know normally if I got a number there, I'm taking that number, I'm plugging in for x, following my order of operations, I'm getting my numerical answer, my value back, right? But now I'm going to put a variable in. Right? A variable represents a value anyway, so same rules apply. If the variable goes in, I get 2a squared minus 3, right? And now that variables are involved, I do as much as I can to simplify the expression. So, simplify that expression. You done yet? You finished? Okay, good. F of a would equal 2a squared minus 3. That's it. So if that makes any kind of sense, we come down here to f of negative x. Take negative x. Plug in up here for x. We get 2 times negative x squared minus 3. So we're dealing with variables. We make sure that our resulting form here is simplified. I can square that negative x. That would get rid of the negative. I'd be left with 2x squared minus 3. Okay, that third part here looks a little more intriguing. Got a binomial expression, right? A binomial expression that we could plug in. So just because it's a variable expression, remember, same rules apply. If that's just a number, that goes in the place of x up here. So as a variable expression, that p plus 2, that goes in the place of x up here. I've got 2 times p plus 2 replacing x, which is being squared, minus 3. Really got to pay attention to the order of operations now, right? Order of operations would state, start with the parentheses, nothing will be done there, but then exponents. So I have to take this p plus 2 squared and expand that out. So what does p plus 2 squared mean? It means p plus 2 times p plus 2. You got to FOIL it. So if I FOIL it, I take p times p first for p squared. Take outside, which is p times 2 plus 2p. Take inside, which is 2 times p plus 2p. I take 2 times 2, my last, get 4. If I combine my like terms and now transfer this back to the problem I'm trying to simplify right here, well, let's see. Let me drop this down a line here because I'm kind of running out of space. I'd have 2 times, transferring this back over and collecting like terms, it would be p squared plus 4p plus 4. Then you got that minus 3. At this point, you can do the multiplication where you distribute the 2 through, right? Once you distribute the 2 through, then you can collect like terms where it makes sense to do so. So let's see if we can kind of do 2 things at once here to speed up the process. You'd have 2 times p squared, 2p squared. You got 2 times 4p, so plus 8p. You got 2 times 4 there, so plus 8, right? Plus 8. And then you could subtract that 3. So 8 minus 3, you got plus 5. Your simplified expression here for what f of p plus 2 would equal is 2p squared plus 8p plus 5. All right, if we look at the last one, on this last one we are taking c plus r. We are inserting that in the place of x in the original function. When we do that, we get 2 times c plus r as a quantity squared minus 3. And essentially what's happening on this problem is very comparable to what happened on the previous problem because we're plugging in a binomial and we're squaring that. So off to the side, if you need to, you take the c plus r times the c plus r. Foiling it, you get c squared. Outside would be c times r, so plus cr. Inside would be r times c, or c times r. Last would be r times r, or r squared. If you combine your like terms here, and you insert back in down here, we get 2 times, that would be c squared. We had a couple of CRs, and we had an r squared. Don't forget the minus 3. It's easy to forget that constant sometimes. But now distribute the 2 through. As we distribute the 2 through, we get 2c squared plus 4cr plus 2r squared, then minus that 3. We have no like terms, so f of c plus r would equal 2c squared plus 4cr plus 2r squared minus 3. So we discussed composite functions last time. We're basically reviewing composite functions now. But since we just discussed how to play with functions on an individual basis with variables, I want to do something very similar with the f of g of x idea, basically. So like we discussed yesterday, we discussed that you're working from the inside out. So I'm starting in here, and based on what we did yesterday, we had an actual number sitting there in the place of x, and we took that and we plugged it in to the function attached, which was g. Now I don't have a number there, I have an x. And as I do other problems, I might have some other variable. But the games still play the same. Take that variable, plug it in to this function. Now obviously, if I'm plugging x in for itself for the function g up here, I'm getting the same thing back. So since I have so many variables involved, I'm going to go ahead and write out what I would get back for g of x here. And I know that that's going to be stuck inside this function notation still. So g of x is going to be x squared minus x minus 4. Basically did a little substitution, right? Now, I am going to take what's inside here that represents a number. I'm going to go to the function f up here, locate my x's, and I'm going to plug that expression of x squared minus x minus 4 in. When I plug that in, it's going to be 2 times replacing x squared minus x minus 4. All of that plus 1. If you distribute your 2 through to clean this up a little bit, you get 2x squared minus 2x. Be minus 8. And that minus 8, I would add to that 1 to make that minus 7. So f of g of x for this problem, based on the given functions, would be 2x squared minus 2x minus 7. All right, we've got g of f of x. So the way this is written out, like we discussed last time, might make more sense to write it as g of f of x, so we can see a little bit better how to work from the inside out. I'm finding g of f of x here. Starting on the inside, we've got this x idea that basically you're plugging into this function f. Of course, if you do that for the function f as it's defined, you're just going to get the same thing back as f is defined. So f of x is, inserting in for x up here, you get 2x plus 1. So 2x plus 1, I substitute in the place of f of x, and I appreciate that I still have to apply this function g overall. Now that I'm ready to apply that function g overall, I'm going to take this 2x plus 1, I'm going to input it basically into the function g wherever I see an x. Right. There's all my x's in my function g. So I'm going to take 2x plus 1, replacing the x's up here. The first x would be squared. Replacing the next x, which I am subtracting. Got to be careful here. Using parentheses would be nice with the substitution so you can keep your signs straight. And then finally, I'm subtracting 4. So there's the expression that ultimately we get that we'll have to simplify. Okay, if I simplify this first binomial squared, and I now reviewed that idea with you, that's the shortcut, right? The shortcut is take the first term and square it. So that'd be 4x squared. The next term is created by taking twice the product of 2x and 1. So twice the product of 2x and 1 would be 4x. And then you take the squared part of the last term. you remember the shortcut, great. If not, you have to FOIL that out. We then take this negative, we distribute through. You get minus 2x, minus 1, minus 4. Minus 4, I kind of jumped ahead there. I misspelled 4, didn't I? Yeah, I misspelled 4. If you combine like terms now, you've got 4x squared. You got the 4x and the minus 2x, so plus 2x. I got a couple ones that cancel, and you're left with minus 4. So there's your expression that represents g of f of x.